Welcome to Alien University, where the engineering department defines academic success by a successful full-scale flight test. For their final design project, Kale and Vex have to build the propulsion system for a dual-purpose spacecraft. To graduate, their ship must reach orbit and then perform complex docking maneuvers once it gets there. The difficulty lies in the conflicting requirements of these two flight phases. A rocket engine optimized for the high chamber pressures and massive mass flow required at launch is poorly suited for the tiny, precise impulses needed for orientation in a vacuum. This table illustrates the massive performance gap. Kale's boost propulsion stage generates millions of newtons of thrust to overcome gravity. Vex's auxiliary system drops to a fraction of a newton to simply move the ship by a single degree. Despite the difference in scale, both systems function as complex circulatory systems. Success depends on their ability to precisely manage the flow of reactive liquids under extreme pressure. Kale selects a cryogenic bipropellant, specifically liquid oxygen and liquid hydrogen. These gases are liquefied at temperatures hundreds of degrees below zero to provide the maximum energy density needed to escape the planet's gravity. This energy is only accessible if the chemicals react in the correct proportions. These formulas define the mixture ratio, the ratio of oxidizer to fuel mass. Kale must calculate these perfectly. An incorrect ratio could spike the temperature, melting the engine. Vex chooses a different path: storable monopropellants and cold gas. These propellants don't require heavy refrigeration, meaning they can sit in a tank for years and restart thousands of times with high reliability. These chemical choices determine the entire mechanical architecture of the ship. The propellant isn't just fuel, it dictates the hardware. Directing attention to the diagrams, these tandem and multi-tank arrangements are typical for large boosters. Because Kale's engine accelerates the vehicle so rapidly, inertia keeps the liquid pressed firmly against the outlet at the bottom of the tank. In zero gravity, Vex's liquid propellant detaches from the tank walls, floating in disconnected blobs. This ullage creates a major engineering problem. If the ship rotates, the liquid can slosh or form a vortex. If a gas bubble enters the feed lines, the engine will experience a sudden drop in pressure, leading to catastrophic combustion failure. To solve this, Vex evaluates the positive expulsion devices shown here. These use flexible inflatable bladders or sliding pistons to physically separate the pressurizing gas from the liquid, forcing the propellant toward the engine regardless of the ship's orientation. Alternatively, Vex can use the surface tension screens shown in this diagram. These fine metal meshes use capillary attraction, the same force that pulls water into a sponge, to keep the engine's intake pipe covered with liquid at all times. In space, managing the fluid inside the tank is as critical as the combustion itself. The propellants must be forced into a combustion chamber that is already under immense internal pressure. This flowchart outlines two primary paths: pressurized gas systems and turbopump systems. Vex selects a gas pressure feed system for the auxiliary thrusters. This regulated pressure path is simple and highly reliable for small engines moving smaller volumes of fluid. A tank of high-pressure helium pushes down on the propellant, forcing it into the thruster at a controlled rate. It's an elegant, mechanical solution with very few moving parts. But Kale's booster requires far more power. To move the massive amount of propellant needed for a launch at such high pressures, a simple gas tank would be too heavy to fly. Kale uses a turbopump engine cycle instead. A small portion of the propellants are burned to create hot gas, which spins a turbine. This turbine drives heavy-duty pumps that shove the liquid into the chamber with thousands of pounds of force. One system relies on the steady push of compressed gas, the other on the violent mechanical power of spinning pumps. It is simulation day at Alien University. Kale and Vex integrate their designs into a single spacecraft for the final test flight. Kale's booster ignites. The turbopumps operate at peak capacity, perfectly maintaining the mixture ratio to generate millions of pounds of thrust as the massive ship clears the planet's atmosphere. Once in the vacuum of space, Vex's system takes over. The surface tension screens keep the fuel steady in 0G, allowing the gas pressure system to fire the precise bursts needed for a perfect docking. Success in rocketry is the result of balancing extreme thermodynamic force with precise fluid management. If you want to see more deep dives into the engineering that powers our world, subscribe to the channel and let us know your favorite rocket component in the comments.
Enroll.